Now we're ready to talk about one of the best parts of rational functions, the graphs. Like this, like this. Or maybe they're like this, like this, like this. They're all over the place. They're crazy. Our goal for this class is really just to be able to graph functions that kind of look like this without a graphing calculator. And so we're going to kind of learn some of the tricks of the trade and spotting some of the key characteristics of one of these rational functions. So it's just going to be of the form y equals ax plus b over cx plus d. And all this means here is that a, b, c, and d are all elements of the real number set, meaning that we've got negatives, we've got positives, we have decimals, we have irrational numbers possibly, but we don't have any imaginary numbers. So a, b, c, d are really most of the numbers, could represent any one of the numbers that we usually tend to work with. Let's talk about what makes up a rational function graph. This is kind of the parent function of rational functions. This is the parent graph or parent function. And it's given by the equation y equals 1 over x. And hopefully this picture looks somewhat familiar to you. If not, let's think about where it comes from. As x gets bigger and bigger and bigger, if I take 1 and I divide it by a big number, that should equal a small number. So as I go this way, as x gets bigger, my y values get smaller. And that should make some sense. Similarly, let's go another color here. If I start to go in this direction with my x values, if I divide 1 by a very, very small number, that's going to get bigger and bigger and bigger, opposite from the other direction. So as x moves to the left, closer and closer to 0, y is going to get increasingly bigger. So that's where this kind of picture comes from. And you notice that I have this vertical asymptote at x equals 0. And again, think about where that comes from. If I divide 1 by 0, if you ever try punching that in your calculator, you're going to get an error, a domain error, or a divide by 0 error rather. And that's because in mathematics, we don't like to divide by 0 because we have this convergence in where this graph should go. Is 1 divided by 0 a large positive number as it looks like it's becoming 1 on this in this direction? Or is it a really, really big negative value? This is kind of an undefined. We cannot have x equals 0 in our domain. This is where these restrictions have come from and why we care about setting the denominator equal to 0. So all these things we kind of keep in mind, and let's talk about the important features that we want to keep in mind of for these graphs. So feature number 1, the vertical asymptote is at x equals 0. This can change, but for the parent function, this is where my vertical asymptote is at x equals 0. There is a horizontal asymptote at y equals 0. Basically what this means is that as x goes to positive and negative infinity, the y values get closer and closer to this value. So as x gets really, really, really big, 1 divided by an enormous number is really, really small, and it's almost 0, but not quite equal to 0. This will never equal 0, but it gets really, really close. And that's what this asymptote means. It's approaching, but not touching that value. X-intercepts. In this case, we have none, but if I move this graph up, down, if I move it up or down, you can see that one of these lines is going to have to cross. So that can happen. We can move these things in order to make x-intercepts occur. And if you think about how do you find x-intercepts, what you do is you set the numerator equal to 0 to find x-intercepts. And we'll see an example of that. Y-intercept, there's none in this case, but to find a y-intercept, you set the x value equal to 0. End behaviors, and this is what we were talking about before, kind of linked with horizontal asymptote. As x approaches positive infinity, y is going to approach 0, and that's what this statement means right here. The limit as x approaches infinity, meaning as my function continues to move towards infinity in the positive direction, the y values get closer and closer and closer and closer to y equals 0, and they don't actually equal 0, and that's why it's called a limit. It is kind of like the ultimate limit, but it won't actually touch that value. So it will never cross 0, it'll never equal 0, but it'll get infinitely close to 0. These are kind of the important characteristics of these functions. So let's kind of put them in place and make a graph of this equation, y equals 1 over x minus 2. First thing to take a look at would be the vertical asymptotes. And these vertical asymptotes occur when with our domain restrictions. So we want to set the denominator equal to 0. So then if I consider the denominator x minus 2 equals 0, I can see that I'll have a vertical asymptote at x equals 2. So let's put that down on the graph. Let me get a dotted line here. And this is basically my domain restriction. X cannot equal 2. I'm actually going to skip over the horizontal asymptote next, and let's talk about the y-intercept. To find the y-intercept, we want to, let's continue with that color scheme. To find the y-intercept, we want to set the x value equal to 0. And that should make sense because x equals 0 is the y-axis. So let's plug in now x equals 0. So y is going to equal 1 over 0 minus 2, which is equal to negative 1/2. So my y-intercept will be at 0, negative 1/2. And let's even label that for good measure. All right, and next let's take a look at the x-intercept. To find the x-intercept, we want to set the y equal to 0. And when we have a fraction, if I set this y equal to 0, let's kind of do this work up here. If 0 is going to equal 1 over x minus 2, really if you think about any fraction, let's kind of sidebar this for a second. If I have any fraction equal to 0, the only way that fraction will equal 0 is if the numerator equals 0. There's no way I can get any fraction equal to 0 unless the numerator equals 0. And you could try it. Try dividing two numbers, try to get it equal to 0. The only way you'll be able to do it is if the first number is equal to 0, or the numerator. So really I'm just looking at the numerator when I'm finding my x-intercepts. And we can see here that 0 equals 1 isn't a thing. There's no number for x that's ever going to make y equal 0. So in this case, there is none. No x-intercepts. This will never cross the x-axis. Now let's think a little bit about end behaviors. We'll talk about the asymptote last because these two things are linked. And I want to take the following two limits. I want to take the limit as x approaches infinity, and I want to take the limit as x approaches negative infinity. And I'm taking these limits of my y values. So the thing that's going on is x is getting really, really big or really, really small, and I'm looking at what happens to the y. If you look at this graph, as x gets bigger, my denominator grows. If I put in really, really large numbers for x, this fraction is becoming really, really small. And it's becoming so small that it's actually going to be approaching 0. And if you're not sure where that comes from, put in some values. Try putting in 100 or 1,000. Let's think about putting 1 over 1,000 minus 2, or 1 over 998. That's a really small number, and that's way over here. So my y values are going to get closer and closer to 0. Similarly, on the left side, I guess I just put that in for negative infinity, but it's actually going to be the same thing for the other side. If I take a really, really large negative number and divide my fraction by a large negative number, that's going to be a really a small number as well. So my limits are y equals 0. So what does that mean? That means that as I'm going towards positive and negative infinity, my y values are getting closer and closer to 0, which really means I have a horizontal asymptote of y equals 0. Whatever that end behavior is going to be linked to whatever my asymptote is. And that's kind of why I left these things to the very end here. These things are linked. So let's put this horizontal asymptote in this picture. So it looks something like that. So now the last thing we have to do is we have to draw this. If you're ever not sure of where these points go, you can always plug in values and see what happens. But this is going to be one of these graphs that kind of has like these two sections, one that's up like this and one that's down. It's kind of hard to do this with the mirror. Something like this. So what I'm going to do then is if I look at this, I have a point in this quadrant of my graph. I'm going to be in opposite quadrants here. And since I have a point down here, it would make sense that I would have something that looks like this. And the opposite quadrant would be something that looks like this. And again, if you're ever not sure where these values come from, or if you're not sure where your points are, just plug some points in. See what happens when x equals 3, see what happens when x equals 4. Actually, as I'm looking at this, when x equals 3, that should be 1 over 1. So really, I should have gone through this point here. But that's okay. This is what my picture looks like. So that was a whole lot of stuff. So I'm going to take a break here, and then why don't you go over any of these notes if you need another look at them, and then we'll try another example in the next video.